Okay, hello everyone. I welcomes to all in our lecture series on ledger physics. In this lecture series, we are discussing these topics, which are most essential for B.sc, B.Tech, M.sc, M.Tech, and various entrance examinations. In our previous classes, we discussed these topics. Last class, we discussed this one, rate equation of four-level ledger system. In this class, we are going to discuss important numericals based upon Einstein's coefficient A and B and whatever the topic we discussed in our previous classes. Okay, so let us start. These things already we have been discussed in our previous classes. Okay, so here I am going to suggest that before you are going to watch this video, numerical video, you go through this topic, Einstein's A and B coefficients and their relations. Okay, this topic is required for today's class because here this is the relation. Boltzmann distribution law. According to Boltzmann distribution law, the number of atoms in a particular energy state at a particular temperature is this one. These two expressions are required for today's class. You just remember this one. And this expression is most important. U mu equal to 8 pi h mu q by cq into this much. And this relation also. Okay. And here in unit dimension we studied this one. A. This A is represents the Einstein's coefficient of spontaneous emission or probability of spontaneous emission, and its unit is a second inverse, and this represents the reciprocal of mean lifetime of a particular level 1 by tau. Tau represents the mean lifetime. This expression is important for today's class, and these three expressions, this one, this one, this one, and this one, you just remember. Okay, now we are going to start today's class, the numericals, more important numericals. Okay, here first question, it is given that find the ratio of population of two states in helium neon ledger that produces light having the wavelength 6328 angstrom at 27 degrees centigrade. Okay, here we are going to use this Boltzmann distribution formula. This one, in a particular energy level, the number density will be equal to n0, that is your total number of atoms, n0 into e to the power minus e1 by kt. E1 represents the energy of that particular level, right? So here same thing, same expression we are going to use over here. I written according to Boltzmann distribution law, the number of atoms in E1 and E2 in thermal equilibrium at temperature T. This is number of atoms per unit volume, not written, but you just you have to consider the number of atoms per unit volume in a particular energy level E1 and E2. Thermal equilibrium at thermal equilibrium T is your N1 equal to N0 e to the power minus E1 by kt. N2 in energy level 2 N0 e to the power minus E2 by kt. So here in question it is asked that we have to find out the ratio of populations. That means N2 by N1 is equal to this term by this term. So here N0 got cancelled, and this term will be moved to the numerator. It will be e to the power minus E2 minus E1 by kt. So here E2 minus E1 is nothing but h mu. This is your E1 and this is your E2. So what is the energy difference? Energy difference is nothing but h mu. So here I substituted instead of E2 minus E1 h mu, right? So here mu is the frequency, can be written as a c by lambda. Here I written c by lambda. C is your speed of the light, 3 into 10 to the 8 meter per second, and h value also you know that is the Planck constant. So multiplying with h and c, we can get this value, right? So exponent of minus 1.96 you can do in the rough itself. Multiplication of h and c, you can get this value by k value 8.5 in 10 to the minus 5 electron volt in electron volt. T is your 300 Kelvin. It is given that temperature is your 27 degrees centigrade, so it will be 300 Kelvin. So you just calculate it and you can found the answer will be 1.1 into 10 to the minus 31. So this will be the correct answer. Okay. Okay. Now we are going to go for the next question. Question number 2. The wavelength given that 6000 angstrom. The coefficient of spontaneous emission 10 to the 6 by second. Determine the coefficient of stimulated emission. That means A given, B we have to find out, and here wavelength of that laser given. So here we are going to use this expression A21 by B21. That means it is given that a two level laser system. Okay, A21 by B21, any particular transition we are going to consider. So for that, A by B will be equal to H by 8 pi H mu q by CQ. Here you can see I told that you have to remember this one. Here A21 by B21, or you can say A by B equal to 8 pi H mu q by CQ. This is the most important expression that you have to remember. Okay. So here we are going to substitute all the values. Here if I am going to put instead of mu equal to C by lambda, here if I am going to put C by lambda q, then CQ got cancel, and in the denominator we can found lambda q only. Right, that implies B21 or B we have to find out. In the question it is given that we have to find out the stimulated emission, coefficient of stimulated emission. That means B21 will be equal to A21 into this will be multiplied with this one A21. It will be lambda q by 8 pi h. You just put all the values. Here A value given 10 to the 6, lambda value given 6000 angstrom, 8 pi value 3.14, and h value 6.6 into 10 to the minus 34. You just substitute and calculate. You can found 1.3 into 10 to the 19 meter square by joule into second square. This will be the answer. So correct answer from this option is your this one. Okay, C will be the correct answer. Next, question number 3. In question number 3, it is given that for a two-level system, the population of upper and lower level are 3 into 10 to the power 18, and in the lower level 0.7 into 10 to the 18 respectively. If coefficient of stimulated emission, that means B given, and energy density, that means U given, the rate of stimulated emission will be here coefficient given, rate of stimulated emission it is asked. That means we have to find out gamma STE. Gamma STE, or the so called rate of change of atoms or molecules of upper level, dN2 by dt, is nothing but your B21 into N2 into U mu. You can check that video. I told that Einstein coefficient video is most important. Here for the stimulated emission, this is value is your B21 into N2 into U mu. Same expression I have been used over here to calculate the answer for this question. So rate of stimulated emission will be B21 into N2 into U mu. All the values has given in the question. So B21, this value I have to substitute it over here. B21, this one. Okay, and N2 is given this one, 3 into 10 to the power 18, and U mu or rho omega, I have to write it itself. It will be good. It will be better. U mu. Okay, energy density means U mu. Here U mu is nothing but energy density. This is also U mu. Wait, I have to write U mu, energy density given this much, 9 into 9 joule by meter cube into Hertz. So we have to substitute all the values. Hertz means 1 by second. Okay, you just calculate this one. You can found 8.1 into 10 to the power 24 a second inverse. Okay, so what will the option in this question not given, so this will be the answer. Right, now we are going to go for our next question, question number 4. In question number 4, it has been given that a two-level system in a thermal equilibrium environment can decay from the excited state by both spontaneous and thermally stimulated emission. At room temperature, means 300 Kelvin, the frequency below which thermal emission or stimulated emission dominated over spontaneous emission is nearest to what is the value it is given. Okay, so here uh, at thermal equilibrium, if I am going to write number of spontaneous emission by number of stimulated emission, or the rate of spontaneous emission by rate of stimulated emission, then what I have to write? I have to write, see here, transition happens from the upper level to lower level, so it will be N2 A2 into N2, and for stimulated rate of stimulated emission we have to write B21 U mu into N2. So N2 N2 got cancelled. So the ratio between uh, here below frequency thermal emission will be dominated over the spontaneous. So ratio between the rate of spontaneous emission by stimulated emission will be this much, right? So this much value will be equal to this much, E to the power h mu by kt minus 1. How? Here I am going to show you. Here A21 by B21 into U mu. Here consider this equation. This one represents the A21 by B21. A21 by B21 equal to how much? This value. Just compare 9 and equation number 8. So 8 by h mu cq h mu q by cq can be written as what? Can be written as u mu into this much, e to the power h mu by kt minus 1, right? Okay, so this is nothing but A21 by B21. So that implies A21 by B21 u mu taken this side. U mu will be equal to this much only, e to the power h mu by kt minus 1, right? Same thing it has been written over there. A21 by B21 u mu. This is u mu. U omega also you can write, no problem. U mu equal to e to the power h mu by kt minus 1. So here h by kt, first we have to find out h by kt. H is the Planck constant, K is a constant, E is your room temperature 300 Kelvin I substituted. So this value we found 1.56 into 10 to the power minus 13. Right. In the question it is asked that at room temperature frequency below which thermal emission, that means stimulated emission, will be dominant over spontaneous emission. So this is the ratio, spontaneous by stimulated. So here if stimulated emission will be dominant over spontaneous, then for a particular frequency mu, this value will be less than 1. See, if stimulated emission dominate over spontaneous, that means stimulated emission value will be more than the spontaneous emission. So obviously this ratio will be less than 1. So we have to find out for which frequency this ratio will be give less than 1. So here in the answer it is given 4 frequencies, right? First we are going to consider 10 to the power 13 hertz. First we are going to consider this value 10 to the power 13 hertz, this value, and we are going to calculate that what will be the ratio between this and this. If less than 1, then it will be acceptable. Okay, so here h by kt, this value h by kt, e to the power h by kt, we found how much? 1.56 into 10 to the power 13 multiplied with mu equal to 10 to the power 13. So it will be e to the power, see, 1.56 into 10 to the minus 13 multiplied with 10 to the 13. So e to the power 1.56 minus 1, right? The e value is around 2.7, right? 2.7 to the power 1.56 100% greater than 1 minus 1, this value we can found greater than 1. So 10 to the power 13 not to be acceptable. Then we are going to consider 10 to the 18. If I am going to consider 10 to the 18 here, already e to the power h by kt value is this much. So this will be e to the power 1.56 into 10 to the power 13 minus 13 into 10 to the power 18. So it will be e to the power 1.56 into 10 to the power 5 minus 1. So this value is so large. Minus 1 means obviously it will be greater than 1. So this frequency also not to be acceptable. Likewise 10 to the 15 also not to be acceptable. But if I am going to consider 10 to the 11, 10 to the 11 means 1.56 into 10 to the power minus 13 is there into 10 to the power 11. So this will be e to the power 1.56 into 10 to the power minus 2 minus 1. So this value is less than 1. So if I am going to calculate this entire value, this will be less than 1. Okay, you calculate it. So the answer will be 10 to the power 11 Hertz for this question. Okay. Okay. Now we are going to go for our next question, question number 5. In question number 5, it is given that the coefficient of stimulated emission, that means B given, for a particular transition is this one, 2.1 10 to the 19, and the emitted photon, the wavelength lambda given 300 angstrom. Then the lifetime of the excited state is approximately what? So two level laser system, this one. So B21 given, lifetime means tau is what will the tau, lifetime of the upper level. So lifetime is reciprocal to the A, coefficient of spontaneous emission. We studied A is inverse proportional to tau, or A directly equal to 1 by tau. Already we studied. I suggest to all of you that at least this topic you have to watch. This topic, Einstein's A and B coefficient, then unit dimension of Einstein coefficient here. In general, A equal to 1 by tau. That we are going to use. And here A by B relation also you should remember. A by B is nothing but this one, 8 pi h mu q by cq. So A B given, from that relation easily we can find out the B given, we have to find out tau. Tau is nothing but 1 by A to 1. So A by B is nothing but this one, 8 pi h mu q by cq. Okay, instead of mu we can substitute c by lambda. So it will be cq by lambda q. So cq and cq got cancelled, and lambda q we can found at the denominator. Now we are going to substitute all the values. So 821 will be equal to 8 pi h by lambda q into B21. 8 pi h value, lambda value given 3000 angstrom, and B value is nothing but 3000 angstrom into 10 to the minus 30. Oh, aega. It will come. If I am going to convert it into the meter, 10 to the minus 10 meter. Okay. So 10 to the 30, because it is whole cube. And B21 it is given that this one, this much, 2.1 into 10 to the power 19. Here this is 10 to the power 19. I am going to correct it. Just wait. This is your 10 to the power 19, right? So the answer you can found this much, 12.89 into 10 to the 6, 8.1. So what will the lifetime? 1 by 8.1. The answer will be 80 nanosecond. So this will be the answer. Okay. See, these questions are belongs to net and get. Net and get. So only for that these options are there. Okay. Now we are going to go for the next question. Question number 6. In figure, three energy level atomic system with Einstein coefficients are this one. So A means spontaneous. This is natural. Spontaneous emission, coefficient of spontaneous emission given from 3 to 2, 3 to 2, this one, 3 to 1, given, and 2 to 1 given, right? What is lifetime of level 3? So lifetime and coefficient of spontaneous emission both are reciprocal, so lifetime is nothing but 1 by a, right? So it is given, it asks that what will the lifetime of level 3. Okay, here given these are things, these are the values a to 1, hence a to 1 means 2 to 1, so tau 2 the value will be this much. Okay, okay. For for com for complete third level, what will the lifetime of level 3, it is asked. No, for complete third level, what will the t3? T3 will be 1 by a32 plus a31, because we have two transitions from level 3. One is from 3 to 2, one is from 3 to 1. So corresponding coefficients are a32 and a31. So 1 by sum of these two terms, we can get this value. Okay, so the lifetime of E3 is equal to how much? We found 12 into 10 to the minus 9 second. Now, can the system provide laser action 2 to 1? 2 to 1, it can it provide the laser action? The question, second bit question, that we are going to discuss uh, here. For that, we have to find out what will the lifetime of level 3 correspond to 2 only. If the atoms will transit from 3 to 2, what will the lifetime of E3? The lifetime will be, for transition 3 to 2 is equal to 1 by A3 to 14 into 10 to the minus 9 second. Okay, then what will the transition or lifetime from 3 to 1? 3 to 1, if I am going to consider, it will be 10 to the power minus 7 second. And here 2 to 1 transition 10 to the power minus 8 second. You just imagine transition from 2 to 1 taking longer time as compared with this one 3 to 2. 3 to 2 is faster, it is slower, it is faster, it is faster. 3 to 2, here you can see 3 to 2 taken 10 to the minus second, so it is faster. And 2 to 1, 2 to 1, it is 10 to the power minus 8, so it is slower, this is slower rate. Okay, and uh, complete third level, if I'm going to consider complete third level, it is also faster, it is also faster. Then if I'm going to consider 3 to 1, 3 to 1, it is very slower as compared with this one and this one. So this is faster, this is slower, it is, this transition is very slow, very slow. That means here we can imagine the transition happens from 3 to 2 is a faster rate, but 3 to 1 with a very slower rate. 2 to 1 slower rate. That means the population inversion can be created in between E2 and E1, because this is the slower rate transition as compared with this transition. So population inversion will be created in between population inversion created in between E2 and E1. If a population inversion created, then this transition can be a laser action or laser oxidation. Okay, okay. Now third bit, at t equal to 0, n atoms centimeter cube are excited to level 3, suppose. Find the rate of change of population of third state. So to find the rate of change of third state, it will be, third state is spontaneous emission, coefficient of spontaneous emission, it has been given, because in between this we found the stimulated emission or laser action. So third state, whatever the transition happens from third state, maybe from 3 to 2 or maybe from 3 to 1, it is spontaneous. So rate of change of atoms or molecules uh, for third level, or rate equation of third level, will be nothing but minus A32N3 minus A331N3, due to which the atoms or molecules is going to be decreased. So only for that it is minus and minus. So A32 value already we Already it has been given 7 into 10 to the power 7. A31 given 1 into 10 to the power 7. N3 not given, so as such it will be there. So the answer will be this one. Okay. Okay. Now we are going to go for next question. This question asked NET 2022. The energies of three lowest state of an atom are this one. That means three energy level system. E naught, that means ground state, have minus 14 electron volt. E1 minus 9 electron volt. E2 minus 7 electron volt. The Einstein coefficients are, that means A1 to 0, this one, A1 0 given, this is spontaneous. A2 to 0, A2 to 0, A2 to 0 means this one, A2 to 0, also spontaneous. And A21, this one is your A21. All the values are given. If a large number of atoms are in energy level E2, here the mean radiative lifetime of this excited state is dash. So 8, 1, 0, 2, 0, 2, 1 given. So the Einstein coefficients of 2 will be the sum of 2 to 0 and 2 to 1, because transition happens from level 2 are this one and this one, right? So the net Einstein coefficient for E2 equal to this much. So A2, if I am going to calculate the value, A20 given, A21 also given. So A2 will be this much, 10 to the power 8. This is your 10 to the power 8. This is 10 to the power 7. So this will be 2 into 10 to the power 8. I have to correct it. Wait. This is your 10 to the power 8, 10 to the power 7. And this is your 2 into 10 to the power 8, right? So A2 we found 2 into 10 to the 8 second inverse. Now the mean radiative lifetime of E2 will be the T2 will be equal to inverse of A2, 1 by A2. 1 by A2 means 1 by 2 into 10 to the power 8. 10 to the power 8 second inverse we can found 0.5 into 10 to the power minus 8 second. This will be the answer. Here also I have to correct. This is 10 to the power 8. Okay. Okay. Now we are going to go for next question. This one. Question number 8. This is also one net question. The electronic energy level diagram of a molecule is shown in the figure. This one. So these are the transitions, stimulated or spontaneous. Here this is transition from 2 to 1. This is 2 to 3, 3 to 4, and 4 to 1. So here 3 to 4, whatever the transition happens, due to which laser light or laser oscillation produced. Okay. So here gamma ij denotes the decay rate for a transition from I to J level. The molecules are optically pumped from level 1 to 2. So 1 to 2 optically pumped. So these are the possible transitions from 2 to 3, 3 to 4, 3 to 4 to 1. Okay, for the transition from level 3 to 4 to be lasing transition, the decay rate have to satisfy what? Decay rate. So these are the decay rate, gamma 21, gamma 23 are the rate of decay from one level to another level. So what satisfy what? There are 4 options here. This transition should be take gamma 34 should be take larger time. Here 3 to 4 transition is the laser action. That means 3 is your metastable state, confirmed. So here 3 to 4 will be minimum rate of transition, and faster rate should be 4 to 1. 4 to 1 should be faster. So where is the options? So here This is the faster, but here last one should be 3 to 4. So this option could not be acceptable here. 4 to 1 should be faster, 3 to 1, 3 to 4 should be slower. Then here 2 to 3, 2 to 3 transition, again second faster. This should be faster. 4 to 1 should be faster, then faster rate should be 2 to 3, and 2 to 1 is your third faster transition, and least faster, or you can say slower rate transition, is your gamma 3 to 4. So यहाँ से यहाँ 3 to 4 जो ट्रांजिशन होगा वो सबसे कम लार्जर समय लेगा, ज्यादा समय लेगा, ठीक है. सो वो मिनिमम रेट ऑफ ट्रांजिशन होगा. बट ये 4 to 1, from 4 to 1 transition should be faster, then only the atoms and molecules will be come down from 4 to level faster rate and again ready to pump to upper level. Okay, so answer will be 4, answer will be C. Okay, okay, here I am going to stop this today's class. These are the important questions belongs to NET and GATE that we have been discussed. It will help you for your exam, for your B.sc exam or your MSc exam, and as well as for any other entrance examinations. In our next class, we are going to discuss Ruby ledger, construction principle of working and application. Okay, so thank you so much for watching this video. Thank you.